Hey guys, today we'll discuss very briefly energy conservation. We should begin with the law of energy conservation, and although many of us have learned this law as energy cannot be created nor destroyed, only transformed, that's okay, that is true. However, we will define it differently in this class, and it goes as follows. Total energy is constant in any process. It may change in form or be transferred from one system to another, but the total remains the same. If we had to define this law using an equation, it would go as follows. Kinetic energy initial plus potential energy initial plus work done by non-conservative forces. I know we haven't talked about that. We will later. Plus the initial contribution of other energies. This could be like heat, nuclear energy, things like that. And that's equal to kinetic energy final plus potential energy final plus the final contribution of other energies. Let's move this so it is centered. Okay, and in fact, let's box this one so we know we're going to use it later. Not now, but later. Okay. There, a little wonky, but that's fine. Okay. And let me just say that potential energy, in this case, it includes both gravitational potential energy and elastic potential energy. So let me just say that this potential energy includes the gravitational potential energy and elastic potential energy. Okay? Normally we use an S for spring. Okay. For this quick lesson, we're going to focus on conservation of mechanical energy. Okay? And that one is simple. We will say that the mechanical energy, so we're going to call it mechanical energy, is going to be equal to kinetic energy plus potential energy. That means this is equal to kinetic energy plus gravitational potential energy plus elastic potential energy. However, today we're not going to consider elastic potential energy. We're going to focus on this one. So if we apply the principle of energy conservation, we will have this relationship. Kinetic energy initial plus gravitational potential energy initial is equal to kinetic energy final plus gravitational potential energy final. Okay? This is true for mechanical energy. When we apply this principle, we are making two assumptions, or two things have to be satisfied for this to work. The first one is that system must be isolated or closed. Okay? No interactions with other objects, forces, etc. And the second one is there is no friction or air drag. Friction or air resistance are included in the non-conservative forces over here. Okay? But today we're not going to take these into account. So we're just going to ignore friction or air drag and we're going to assume the system is isolated. Okay, let's do the example now. A 500 kilogram pig is standing at the top of a muddy hill on a rainy day. The hill is 100 meters long with a vertical drop of 30 meters. The pig slips and begins to slide down the hill. What is the pig's speed at the bottom of the hill? Okay, let's draw the situation. So let me start with the ground level. I always want to have ground level when I do these type of problems. So let's say this is the ground level, okay? So let me draw the hill. Okay? And then we know that it is 100 meters long. So we're going to say from here to here. This is 100 meters. You'll see that this number is irrelevant when we apply energy conservation. Then I'm going to establish my zero line. So I'm going to say this is y is equal to 0. Okay? And then I'm going to model the pig, let's do the blue pig, as a particle. Okay? As a particle. And then he's going to slide down, and I want to know the velocity of the pig at this point. I'm going to call it V final. I know we use just V for final, but I think for energy is good if we use V final. Okay? So now let's write down the given information. We know the mass of the pig. That's 500 kilograms. And we know the hill is 100 meters long. At this point, I don't really care about it. You'll see why. So I'm just going to skip. And then I have a vertical drop of 30 meters. Okay, because we're going to apply energy conservation in the initial and final quantities. So because this is my zero line, then that means this should match my initial height. Okay? So my initial height is going to be, HI for initial, 0 meters. That means my final height is going to be 30 meters. Okay? Because the distance from here to here is 30 meters. So my initial height, which corresponds to my zero line, is 0, and my final height is 30 meters. So H initial, 0 meters, height final, 30 meters. Then I know that the pig was just standing, it wasn't moving, therefore the initial velocity of the pig is 0 meters per second, and then the final is what I'm trying to find. And I also know that the acceleration of gravity is 9.8 meters per second squared. Okay, we could solve this problem using kinematics. We could use forces. However, let's apply energy conservation. Some problems say using energy considerations. We're going to apply energy conservation pertaining to mechanical energy. That principle says kinetic energy initial plus gravitational potential energy initial is equal to kinetic energy final plus gravitational potential energy final. Let's think about it. Because the pig is not moving at first, it's just standing, and the initial velocity is 0, that means we don't have any kinetic energy initially. There's only potential energy, right? Energy of height. Then at the bottom, when we reach a zero line, there is no height, right? Oh, I have these two mixed, okay? I have these two mixed. So I should have, this should be my initial height, right? Because the pig started here. And this should be my final height. So let's fix that real quick. Let's fix that real quick. There you go. So at the bottom, my height is 0, which means I don't have any potential gravitational energy. Now I just have to substitute my equations. So the initial gravitational potential energy will be mgh initial. And then the final kinetic energy is going to be 1/2 mass times velocity final squared. So there is what we're looking for. We're looking for final velocity. Notice that the mass will cancel. And now we have gravitational acceleration times the initial height is equal to 1/2 times velocity final squared. We just have to solve for final velocity, multiply times 2 to get rid of the fraction, take the square root, and then use the reflexive property. That means I just flip my equation. So my final velocity is equal to the square root of 2gh initial. When I plug in my numbers, I'm going to do the square root at the end. So I have 2 times 9.8 meters per second squared times 30 meters and then I already did it in decimals. So my answer would be 24.248. Let's round to 25, okay? So my final velocity is going to be 24.25 meters per second. Okay, there you go. That's it.